There are many of them, actually. There's in many different fields, but this is the one for mechanics. 1960 in translation. I don't know when it was first published. So in a certain sense, it's out of date. On the other hand, mechanics hasn't changed a hell of a lot of classical mechanics for the last 100 years, except for the addition of chaos and so on. But you notice how thin it is. It is a beautiful book, and their presentation is of many topics is really wonderful because it's theoretically clean and deep. What the book lacks, I wouldn't use it. Pui and I have fought about this in the past. Pui has taught the course from that, and I claim that's bad for the students because you don't get good preparation for the problems and so on, because it is kind of thin and it is very theoretically oriented. And you need more like Goldstein to cut your teeth on the problems such as will be on the qual and so on. But for beautiful presentations, and the nicest presentation I know of is what I'm going to show you this morning. This to me is almost like bloody magic, because what I'm going to show you is how we start with one simple assumption about the Lagrangian, about the principle of least action, and we derive everything else that you know about modern mechanics from there. When we don't even know what the function is, we only assume that there is such a function. So this is pretty amazing. Okay, so we'll start with a system of n particles in space. We have n particles, and we can spend time talking about what we mean by a particle, but we will take them to be everybody's common notion of a point particle. And that there are 3n degrees of freedom. These don't have to be described in Cartesian coordinates, although we love to generally write down x, y, and z, but we maybe will write other coordinate systems like cylindrical and spherical and God knows even elliptical and all the other heinous sets of coordinates that you'll see if you look at some of the older textbooks, but nobody ever uses. But generalized coordinates we will use for sure. Generalized coordinates can be practically anything. For example, a simple example is you have a car on a little track, and you can describe the distance along the track as s, for example, and we can break down the discussion. We could give the height at a given s, for example, and we could have a set of coordinates that identifies uniquely where the roller coaster is at any point in time. Now comes the one magic trick in this, which is something that I confess to not truly understanding, and I think none of my theoretical friends do really either, which is, and our friends here say, if all the coordinates and velocities are specified simultaneously, it is known from experience that the state of the system is completely determined and that its subsequent motion can, in principle, be calculated. So we write down a set of q, we call these general coordinates q and q dot. And so in this case, we would have six coordinates 6n to define the system at any given instant. And this set of variables define the motion of the system. Now I may be going to add in some things like the potential and so on a little later on, but the thing is that, as I mentioned last time, that I don't have to tell you what, say, Q double dot is at every point in this system, or Q triple dot. I only need Q and Q dot. If you look a little puzzled, that's it. It's not obvious, but it's usually completely swept under the rug. So the essential assumption to get started on all of this is that these two things are good enough to determine the whole motion of the system. This is a fact of the universe. But I'll tell you something that we're going to derive about these principles about the Lagrangian and the equations, the Lagrangian equations of motion. They turn out to have a much wider applicability than just mechanics. Turns out that this kind of mathematics is useful in describing lots of things. People have written down the Lagrangian of the stock market and do crazy things like this. And it seems that this mathematics has some very wide application. And as I say, I confess I don't really understand why. How come it is so wide in the world that the Q and Q dot is good enough? It certainly would have been, things would have been a lot messier had we needed Q double dot, Q triple dot, who knows? And it's not just, as someone suggested last time, a first order approximation. But as far as we can tell, those other terms are not needed. And until then, life gets complicated when we start talking about quantum mechanical field theory. So that is the first assumption. So then the very beginning is that we define something called the action. Some function of this L that we defined, the Lagrangian, we call it the Lagrangian. We don't at this point know what it is. All we say is that there is a function of Q, Q dot, and T, which will be a minimum, actually an extremum, in going between points Q1 and Q2. And this path can be annual path. And the action is by definition, the integral of this as yet unknown function L of Q, Q dot, and T between those 2 points. And the 2 points are fixed. And we need this, although later it can get relaxed, that it has to go between 2 fixed points.
So is this in like a coordinate space or configuration space? You're talking about a path between one point to another. What kind of space are you talking about, I guess?
Well, it could be X, Y, Z, but it could be something else. It could be along the roller coaster.
Just be so like configuration space of the system then?
Something like that. So now, to show that it's a minimum, we have to use variational calculus. And probably people have had variational calculus in mathematics. Yes, no? But at any rate, you don't need to know too much about it. and the way, as usual, the way the mathematicians teach it, it's going to become burdened with all kinds of qualifications and so on. But the usual way then is we say that we can add to Q of t this kind of delta Q of t. This is a variation. And that delta is not just adding some fixed number to it, it's a function. So when we're talking about variational calculus, we're talking about varying functions, not just varying, you know, dx, dy around a little point. We're talking about screwing with a whole function. So I'm saying then that I can do some variation on this path by some, and I don't mean this to be a constant offset, by some delta q, some function delta q. Could be more complicated, could be like that. You can get me in trouble by asking, what about things that do ugliness like that? Well, then we can cut that guy off there. But also the function has to be marginally well behaved. And as usual with these sorts of things, basically any function that you will run into in a natural situation, that is to say that is differentiable, that has a finite number of discontinuities, and is differentiable at every point, or at least most every point. In general, you don't need to trouble yourself about it. Most any function will work. So you can think about the variation. In fact, a good way to think about the variation, and one of the simplest demonstration is the points, the straight line being the minimum between 2 points, is I can make my variation be a sine wave. And higher order terms, so I can compose bloody any function you want, right? By adding up terms from this, a Fourier transform of some arbitrary shape between these two. I can add them up out of sines and cosines. In this case, since I fixed to the ends, it would be sines. And then that is my variation will be the sum over the Fourier components of that. And so what I will show with the variation is that those components are all zero, and that a straight line is the shortest distance between 2 points. So that's the way the game works. But right, and so we have delta of Q1 is equal to delta of Q2. The fixed point at the end is equal to 0 because we defined it that way. We said that it was fixed. And it is an extremum, but not necessarily a minimum. I'll come back to that in a little bit. So I can replace S, the change in S, delta S, is equal to an integral T1 to T2 L of Q plus delta Q, Q dot plus delta Q dot, and T dt minus just the normal, the unperturbed version. So the principle of least action then comes down to saying that delta of the L is 0. And so we can expand that. We can expand that by writing delta S is equal to dl dq dot delta Q from T1 to T2. I'll come back to this in a moment. T1 to T2 dl dq. I have to keep my partial and complete derivatives straight here. Now, this comes from, so I'm just going to write this as the time derivative of this term, the whole time derivative of this term, and then I'm integrating by parts, so this part stays here, and this part becomes the integral piece. But this is going to be 0 because, by definition, dq is 0 at the endpoints. So that term drops out. And there we have, we've suddenly got, we're already home and dry with Lagrange's equations. It's kind of, you feel like you've been cheated, we didn't do anything. All of a sudden, after you read through all of this murky stuff in the book here, and finally, after D'Alembert's principle and so on and all that, you get to it. But in fact, it's just a couple of steps to say that there is some function, I don't know what by the way, I'm sorry, I keep writing, I prefer to write the Lagrangian as a script L, but don't that confuse you. That we find that we've already got Lagrange's equations, and here they are. d dt dl dq. Come back to that in a moment. dqi is equal to 0, and I is equal to 1, comma, blah, 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 whatever. S in this notation, variables. So it's true for one, if it's true for one component, the argument is, if it's true for one component, here it's true for all components, and true for them independently. Has to be, because each one of these has to satisfy that equation. So here we are. Put a big box around it. I just love the way this is just kind of pulled out of a hat. And we haven't even begun to consider what is L. We didn't have to go through all the other hanky-panky. We haven't said anything about Newton's 3 laws yet. We haven't said that they were true. We haven't said anything about F equal ma. The only thing that we said about the dynamics of the system so far was that that's all we need to define the system. We nail down those points, those variables at that point. The system is thereafter defined. Okay, so now another of these, in the mathematics courses that always go through that this function, whether additivity and multiplicativity applies and all that sort of thing, but it's very useful here. So we can, I can go through the argument a little bit more, but it applies to each particle, and it applies to an ensemble of particles as well. We just add them all up, and we can define two different systems of particles. Have in the back of your mind that we have a set of particles here, which we call A, and a set of particles over here, which we call B, and they're a long ways away. What does a long ways away mean? A long ways away means they don't screw with each other much. The interactions between them are negligible. We can put them far enough apart. And we can write down a Lagrangian for A and a Lagrangian for B. And so we can therefore argue that the limit of L is equal to LA plus LB. That the total Lagrangian is the sum of the two individual Lagrangians. We moreover, so you can see what's coming out of this. What's coming out of this is because we're going to have something called a mass introduced. This says that you can fuss with that there's something in between LA and LB which is the same. It's a coupling constant. It's the mass, in fact, as we'll get to. We can also multiply. We can multiply some constant times L, and it will be a perfectly valid L prime. But what this says is that if I'm going to have this true, if I'm going to multiply one of these guys by A, I got to multiply the other one by A as well. And so it's maybe a little subtle point, but it's an important one, and I'll come back to that again later. There's another further tricky remark, which is that I can write a new Lagrangian of Q dot and T, which is equal to L of Q dot and T, plus any old time derivative, which is some decently nice function of Q and T. And if I do that, I will get the same equations of motion. Because this thing is going to disappear. And so let's just write that down. The S prime in this case, which will be then the integral of the L prime, is equal to T1 to T2 of L of the usual one, Q dot and T dt, plus the integral from T1 to T2 of this function df dt, which is a whole derivative, so we're done. So it's just then this piece plus this piece is just f of Q2 and T2 and minus f of Q1 at time 1 and T1 those values at the